Hey guys, in this video we're going to be constructing a differential equation from just a general function, and then we're going to see if we can get that function. So, in other words, let's try and make a differential equation with just this simple polynomial here. So, y equals 6x cubed. Now, to make a differential equation, you need an equation pretty much with derivatives in it. So that can be either first derivatives, or second derivatives, or third derivatives. But it doesn't really matter as long as there's a derivative in it, pretty much. So what we're going to do is find its first derivative. So dy dx, bring the power down the front and subtract the power by 1. So 3 times 6 is going to be 18. So x and then squared. Alright, the second derivative, so dy dx or squared, is going to be, bring the 2 down the front, so it's going to be 36x. Okay, so let's try and construct the differential equation. So let's just say, alright, let's see how these things relate to each other. So a differential equation I can think of is pretty much, alright, the second derivative multiplied by x minus twice the first derivative would be equal to 0, wouldn't it? Because, alright, if we were to substitute this bit into here, we'd have, let's say, what would that be? That would then turn into 36x squared. And then, what about this bit? So we had this bit, this is first derivative, put that in here. What do you get? You get negative 2 times by 18, which is negative 36 x squared is equal to 0. 0 equals 0. Boom. This is a differential equation we've just made from a simple polynomial. Now, let's see if we can go backwards. Let's say we didn't know any of this, but we just got given this. Could we work out our polynomial? Well, let's see. So, let's rewrite it. Like, let's say, we'll move it to the side for real quick. And let's just move this up here. And let's get rid of all this because we don't need that anymore. Okay. So, what should we do to start off? Well, we've got to pretty much take a look at pretty much the second derivative here. What does this mean? The second derivative is the derivative of the first derivative. In other words, d squared dy over dx squared is equal to the derivative of dy dx. So this is a little property we can see here. So if we made a substitution, we could turn this into pretty much, instead of a second order differential equation, instead of having a second derivative, with a substitution we can make it into pretty much a first order differential equation where it's only got one derivative in it, the first derivative. Let's say, alright, let u equal dy dx. Now, why can we do this? Well, for starters, instead of having a derivative here, it turns into a variable. And instead of this being a second derivative, it turns into a first order derivative. Because if we replace, let's say, this bit here with u, then all we're doing is the derivative of x with respect to u, which is just du dx. So we can rewrite this differential equation like this. Now, we don't have to change our x at all. The x still stays there because we've still got x. So we have x du dx minus 2u equals 0. Now this is a lot easier to solve. All we're going to have to do is separation of variables. Now, before we keep going, we need some initial conditions. So, when x is equal to 0, y is also going to be equal to 0. And when x is also equal to 0, the first derivative will also be equal to 0. So the reason we need that is because if we want to get a specific polynomial, we're going to have to get rid of our plus c's pretty much. Okay, so how do we solve this here? Well, we'll move this term over to the other side so we can pretty much rearrange it and get our variables on one side. So we'll have x du dx is equal to 2u. Now, we want to get all of our du's and u's on one side and all of our x's and dx's on another side. Basically separation of variables. So what I'm going to do is I'm going to move the dx up here. So we're going to have x du equals 2u dx. And what I'm going to do now is I'm going to divide both sides by 2ux. So 2ux. So in other words, that cancels and that cancels. So what we're left with is du over 2u is equal to dx over x. Now you can see we've just done separation of variables. So what we can do is integrate both sides. You can see we've got a constant here, so we can take the constant out. So a half, so the integral of just du over u is equal to the integral of x, dx on the top. Okay, so if you recall, the integral of 1 over a variable is just going to be log of that variable, natural log. plus a constant. So what we're left with is a half log of the absolute value of the variable plus c. Now, this half would act on all of this here, but I'm just going to leave the half at the front because this half multiplied by plus c will just be another plus c. So what I can do is pretty much just write it like this. So the half is only affecting the log because the half, let's say, already affected the plus c to give another plus c. And this can be log of x. Now I would write a plus c, but we can move it to the other side and it would be another plus c. So we're only going to write one plus c. Okay. Now, this is where our substitution comes in again. So, what was u? U was dy dx. What do we get told? When x is equal to 0, y is equal to 0. And when x is equal to 0, the first derivative is equal to 0. So, we want to get rid of this plus c. So the way we do that is pretty much, alright, we're going to put this guy into here. So we will have everything as normal again. So half natural log of the absolute value of dy dx plus c is equal to log of x. Okay. Now we're going to substitute our initial conditions in. So when x is equal to 0, dy dx is equal to 0. So we have a half log of 0 plus c is equal to log of 0. That's 0. That whole thing's 0, so c must be equal to 0. So in other words, what we're left with is pretty much a half natural log of dy dx is equal to natural log of x. Now, you know pretty much our log laws, we can bring this power up here. So what we have is natural log and a half, something to the power of a half is the square root. So square root of dy dx, natural log is equal to natural log of x. Now, if you're logging something on this side and you're logging something on this side, effectively, these two things must be equal then. So what we're left with is the square root of dy dx is therefore equal to x. Now, if we square both sides, we can get rid of this square root. So what we're left with is dy dx is equal to x squared. Now, that looks very familiar to what we have up here. Now, all we got to do is integrate both sides with respect to x. So y is equal to the integral of x squared dx, and then what we're left with is y is equal to a third x cubed plus c. Now we know when y is equal to 0, x is equal to 0, so therefore 0, 0, c must be equal to 0, so therefore y is equal to a third x cubed. Now you're probably thinking, why didn't we get this? Well, let's take a look at what we did get. So let's move all this to the side, and this is basically where we're going to see pretty much a property. Well, a little pattern in this polynomial. It doesn't matter what constant we have at the front here. So what we got was y is equal to a third x to the power of 3. dy dx of that is just x squared. And the second derivative of that is just going to be 2x. Now, can you see the difference between this constant and this constant is times by 3? Same as with this constant and this 1 here. It's also a times by 3. And what's the difference between this number and this number? It's a times by 2, as well as this is. So to be honest, it doesn't really matter what we get in front of here. This is a solution, and so is this. As long as it follows this ratio, pretty much. It doesn't really matter what you have in front of this. So you can pretty much have, alright, y is equal to ax cubed. That will be a solution to, what is our differential equation here. Because the next derivative of that will be 3 times as big, and the second derivative of that will be twice as big as the first derivative, because you're going to have this 2 come down the front, so you have 6ax. So to be honest, this is the more general solution. Righto. I hope you guys enjoyed that video. All we did was just play with a couple of derivatives and we got a good understanding out of it. Righto. Thanks for watching. I hope you enjoyed.